Well, now, please, we'll hear the presentation about the CTBT IMS, A Window into a Century of Global Soundscapes, 1920-2020, by Michael Ainsley.
Okay, thank you. Thank you everyone for being here. My name is Michael Ainsley, and my talk is about the evolution of the global soundscape since 1920. My co-authors are Stephen Robinson, Peter Tyack, Rex Andrew, Peter Harris, Michelle Halverson, and Alex McGilvray. So those of you who have a background in underwater acoustics will recognize the graph on the right-hand side of this picture. It's from a classic paper by Gordon Wentz in 1962, where he divided the ambient sound spectrum into different categories, and what's shown here is primarily contributions from wind on the right, shipping in the middle, and bottom left, I should say, and then seismic contributions on the top left. And I'd like you to focus your attention on the red curve here, which Wentz labeled as usual traffic noise hyphen deep water. And if Wentz were here today, I would ask him this question: how did you know that that curve was generated by ships? This slide describes the structure of my talk. The background is what I just showed you, the Wentz curves. The middle part of the talk is talking about building up a global sound energy budget, starting with a nowcast, by which I mean a model based on IMS measurements for 2020 of how the sound energy is distributed with frequency. And then to look back in time, back to 1920, you're probably wondering how one does that. Well, you build a theoretical model that matches the nowcast, and then basically back propagate, if you like, in time back to 1920. And then I'll come back to, in the last part of the talk, to revisit the Wentz curves. And if time, I'd like to say something about earthquakes, but I fear I won't have time for that, but we'll see. So this is the hydrophone network. We used 8 hydrophones from the IMS, supplemented by 3 hydrophones from some Northeast Pacific stations. In total, that's 11 hydrophones. They each represent, if divided equally, 100 million cubic kilometers, and that's what I have in mind when I use the phrase geographically sparse. The graph on the right shows the sound energy spectrum. The black curve is the total sound energy as a function of frequency. These are in 1/10th decade bands. The way that the sound pressure is used, the sound pressure measurements are turned first into RMS sound pressure, and this RMS average over a long period of time. And that RMS sound pressure is a measure of local energy density, local sound energy density. That sound energy density is then converted into total energy in a basin simply by multiplying by the volume of that basin, the basin that that hydrophone is representing. And you can see that the largest contribution comes from the North Pacific Ocean. That's the red curve at the top. The second largest contribution comes from the North Atlantic. And you might be thinking, wait a minute, there are no hydrophones in the North Atlantic. And I have to say you'd be right. So how did we do that? Basically, it's partly an extrapolation from the North Pacific, and partly a single snapshot of one glider measurement that we did have in the North Atlantic, and that was used to build up the North Atlantic. And then we have the South Pacific, which is a long, long way down in terms of the total energy, except at low frequencies, which I'll come back to. That's where the earthquakes are important, and that contribution at low frequency, that's all from Juan Fernandez, coming from the Atacama Fault. Okay, so those are the measurements. What about the model? The model predictions need some estimate of the source spectrum. The main sources that contribute in this frequency range are whales and ships. On the top there, you see the source spectrum of baleen whales in green. The lower graph shows the source spectrum of ships. The blue dashed line comes from is the source level spectrum of container ships. The blue dotted line comes from tankers and bulk carriers. that information about the source spectrum is fed in, combined with the knowledge of the number of sources, which we know, and the critical angle, which is a measure of the range of angles that's trapped within the ocean. And that's fed into a theoretical model to compute then the total sound energy from each of those sources. The shapes look similar, but instead of measuring the source information, we're now measuring the total energy in joules, and what's plotted on the y-axis in both of these cases is the total sound energy in each decadecade band in joules, from green from whales, in blue from ships. And the obvious thing to do, once you've got sound energy, this is a linear quantity, you can just add it. So if you want to know how to combine the whales and the ships, you just add them together. And you can see on the right there, the black curve is the total sound energy, the blue curve is the contribution from ships, the green curve is the contribution from whales. And if I now put that alongside the measurement, you can start to see some similarities. You can see that there's a peak in the 20 to 25 hertz frequency range, which is coming from whales. There's a much broader peak at higher frequencies coming from ships. And then there's that funny spike at low frequency, which comes from earthquakes. We don't have a model for the earthquakes. So now the hindcast. This is the hard part, you might think. But actually, it's not so hard. We have exactly the information that we already have, which is the source spectrum, the information about the critical angle. The only thing missing is the number of sources. And it turns out that if you Google for the number of whales, you find that there's information published by IUCN. If you Google for the number of ships, you find out there's information published by the UN Trade and Development. So we have all the information we need. All that picture, that graph there shows the number of fin whales at the top in green versus time since 1920. The lower green curve is the number of blue whales, and you can see how they were both were decimated in the early half of the 20th century. And the two blue curves are basically as the number of ships rising steadily. The lower one is container ships. The upper one is the other ship, all other ships. And the process of converting to a sound spectrum is exactly the same. There's no difference here, but I'm just doing it as a function of time. And you can see now, with time coming out of the page from 1920 to 2020, you can see that the upper graph is from ships, and you see it doesn't actually change very much in shape. It just increases a little bit in level. The lower graph from whales, you can see the dramatic decrease in time, which results purely from the dramatic decrease in the number of whales. And we added them before, we can add them again. This is still sound energy. They add linearly. Top left is the contribution from ships. Bottom left is the contribution from whales. On the right, you see what happens when you add them together. And you can see very clearly that today, in 2020, most of the spectrum is dominated by ships. There's a small contribution which is dominated by whales, around 20 to 25 hertz. But if you go back in time to 1920, you see the reverse is the case. Almost all of the sound energy is coming from whales. Okay, so one thing I forgot to mention in one of the earlier slides, the Wentz curve that I started with, is that red curve that I drew by hand on it had a peak at around 30 hertz. And this graph now is actually showing that same peak at 30 hertz. It's exactly the same curve. It represents the upper bound of the red smudge that I drew. So that's what we're aiming for. That is the Wentz curve for so-called, in his words, usual traffic noise in deep water. The blue curve is a measurement from Wentz's own work of ambient sound at the same location as the Wentz curves are applicable to. But at a time of year when there are no baleen whale, out of the baleen whale calling season, basically. So this is when you expect ships to dominate. And you see that, I believe ships do dominate, but they contribute at a much higher frequency, between 50 and 60 hertz. And that's confirmed by the theoretical model from the hindcast, which shows a peak at somewhere between 50 and 60 hertz. So the ships are peaking at a higher frequency than the Wentz curve is suggesting they should. And I see I'm running out of time. The top graph here is the same as the one I just showed you. The lower one shows the shows the effect of the baleen whales. You can see the blue curve is now Wentz's own measurements, including during the baleen whale calling season, and the black solid line is showing the theoretical contribution from ships and whales together, showing a big peak again at the blue whale calling frequencies. And what is this? I'm confused. Is that, no? Yeah, yeah, sorry. So basically, in a nutshell, the curve that's Wentz was saying corresponds to deep water shipping doesn't. It doesn't come from shipping. They come from whales. I did say I wanted to say something about earthquakes, but I don't think I have time. But I will just say one thing, that the peak you see there in the 2000s, there's a big, strong peak in the amount of power coming from earthquakes. That's the peak that the previous speaker was talking about between 2004 and 2010. That's not a representative period. There's very, very powerful earthquakes during that time that were not appearing at other times. And so just briefly, conclusions. Baleen whales dominate at low frequency. Ships dominate at high frequency. The Wentz curve for deep water shipping doesn't come from ships. It comes from baleen whales. And if you look at if you look at the actual complete spectrum, you see that the whales spectrum is basically caught between earthquakes at low frequency and ships at high frequency. That's the end of my talk. Thank you.
Sorry, any question? Yes, please.
Did your analysis take into account any difference in the average power output per ship, or was it just simply the number of ships multiplied by a standard? Just thinking older ships would have, I would imagine, more noisy machinery.
Yeah, so I'm not completely sure I understand the question, but for each category of ships, each category of ships is attributed a particular source spectrum. Mm-hmm. We don't have a distribution of spectra. We just have an average spectrum. And if that average spectrum is representative of that category, then the averaging will take care of any variations.
So an oil tanker from 1950 would have the same power output as an oil tanker from today?
Right, no, okay, now I understand your question. Yes, that's an assumption that we make, yes.
Okay,
yeah.
Thank you.
So thank you very much.